In this video, we're going to look at the basic rules of probability. Now that we have a foundation to work on, we can start getting into some more complex probabilities and finding those answers. So we're going to be understanding what type of a number a probability can be. And then we're going to look at more complex probabilities using unions, intersections, and complements, combining our ideas of set theory and probability theory. So first of all, how big or small can a probability be? Let's remember that a probability is the likelihood that something can happen. We should know that the likelihood of something happening cannot be less than 0%. Doesn't make sense to be a negative percent that something happens, or greater than 100%. Even though colloquially we often say something, 1,000% sure about something, it doesn't actually make sense. It can only be 100%. So given an event E, we know the probability of that thing happening, probability of E, has to be at least 0 or at most 100%. We are often going to be thinking about these percentages as decimal forms. So they're going to be numbers in between 0 and 1. So therefore, we're often going to think that a probability of an event is in between 0 and 1, including those values. And we often represent probabilities as fractions because of that. For instance, like 1/2 instead of 0.5. There's a couple rules that we've already kind of talked about, but we're just going to say clearly now. The probability of the empty set, that is an event, the empty set, is 0. That is an impossible event. The probability of the empty set is 0. The probability of the sample space, the entire sample space, that means everything that could possibly occur, is 1. It's 100% of the stuff. This is a certain event. And as we said, the probability of any event is in between 0 and 1. So now let's get into some more complex problems. We're going to be introducing some ideas of set theory, unions, intersections, and complements. So first, two events E and F are said to be mutually exclusive if they both cannot occur at the same time. In other words, E and F are mutually exclusive if E intersect F is the empty set. And this is a term that we brought up in set theory, just with now a slightly different context, thinking about events instead of sets. But since events are actually sets, it really is the same term that we're using. So let's look at an example of mutually exclusive sets. So we're going to roll a die, a 6-sided die, and we're going to let the following events be defined. E is the event that an even number comes up. F is the event a number greater than 3 comes up. And G is the event an odd number comes up. So our questions are E and F mutually exclusive, and are E and G mutually exclusive? And it might help to write these sets in a set notation. So E is an even number comes up. That means the possible outcomes are 2, 4, and 6. F, a number greater than 3 coming up, is 4, 5, and 6. And G, an odd number comes up, is 1, 3, or 5. So the question, are E and F mutually exclusive? Well, we think about what's the intersection between E and F. Intersection between E and F, that is 2, 4, 6. And F is 4, 5, 6. And those do not have an empty intersection. That intersection is both 4 and 6. It's the things that are in both those sets. So the answer is no. E and G, however, if we look at their intersection, E is again given by 2, 4, 6, and G given by 1, 3, 5. There is nothing in common between those two sets, so the empty set is the intersection, so these are mutually exclusive. And note that we can represent these sets using Venn diagrams, something we're going to look at later on in this video some more too. So let's look at the set E, the set F, and the set G. And we're going to place all of our 6 numbers into this Venn diagram. So note that if I place the number 1, that is just in G and not in E and F. The number 2 is just in E and not in F and G. 3 is just in G. 4 is in the intersection of E and F, but not G. 5 is in the intersection of F and G, but not E. And 6 is also in the intersection of E and F, but not G. So we can place all of our possible outcomes in a Venn diagram and say something about all of those things as well. And we can see that E and G don't share any numbers together, therefore they're mutually exclusive. So next we're going to think about a more complex probability problem, and that is rolling a pair of dice. So here we're going to roll 2 dice at the same time, and we're going to look at the sums of those dice. And the first question is, can we find the sample space of this experiment, rolling 2 dice at the same time? Well, I'll let you think about it for a little bit if you haven't thought about it before, but the possible sums of a pair of dice are the numbers 2 through 12. That's everything you could possibly have when you roll 2 dice, 6-sided dice. But these are not equally likely. And because of that, we're not going to have this as our sample space, because the sample space is going to be equally likely outcomes. So to understand why these are not equally likely, let's answer the question, how many different ways can 2 dice give a sum of 7? So we have the numbers 1 through 6 to play with on both dice. And it might also help to think about 2 different dice here. You know, maybe we have a red dice and a blue dice here. And we're going to roll them together. So we could have a 1 on the red dice and a 6 on the blue dice. 1 on the red dice, 6 on the blue dice. We could have a 2 on the red dice and a 5 on the blue dice. And we could have a 3 on the red dice and a 4 on the blue dice. And it's a good question to ask, what happens if I roll a 4 on the red dice and a 3 on the blue dice? Is that the same thing as rolling a 3 on the red dice and a 4 on the blue dice? And I think this is where it's important to think about 2 separate dice that we're dealing with. If I didn't say these are 2 separate dice, that might be a more complicated question, right? They're the same, they're kind of they're equal dice, they're the same dice. There's nothing different between them. So does it matter if one dice is something or the other? But if you think about them as different colors, I think it's pretty clear that that's a different thing that could happen, the red dice being 3 or the red dice being 4. So these are not the same thing. So we're going to think about them in a different way, as a different outcome. Similarly, we could have the reverse of the other 2. We could have a 6 and a 5 on the red dice and a 1 and a 2 on the blue dice. And that's all the different ways we can get a sum of 7. There are 6 outcomes here. And if we think about our outcomes as these ordered pairs, right, of red dice, blue dice, or first dice, second die, We can think about all the different sums we can have, and we can see that some are more common than others. In fact, 7 is the most common sum. There's 6 outcomes. And 2 and 12 are the least common. There's only one way that you can get that. So total, how many things are in this sample space? Well, again, we can just count these up, and you can do that if you want, but we can use some counting measures. We have ordered pairs, 6 numbers in each. We can say that the size of the sample space here is going to be 6 options for the first dice times 6 options for the second dice is going to give us 36 total options. So the size of the sample space is 36 things, and we've kind of listed them out in this table right here according to their sum. All right, now with that in hand, let's answer some questions about the probabilities here. So a pair of dice is rolled. Find the following probabilities of the following events. The sum is 7. Well, we found that there are 6 outcomes with a sum of 7. And there are 36 total outcomes. So the probability here is going to be 6. We call this a E here. The probability of E is the size of the set E over the size of the sample space. That's going to be 6 over 36, or reduced to 1/6. So if you're rolling 2 dice, you should expect that 1/6 of the time you should get a 7. Now let's look at the event. The sum is greater than 9. We'll call this event F to differentiate it from the previous one. Well, again, we know there are going to be 36 total outcomes. Everything we're going to have is going to be over 36 here. Let's go back to the previous page and think about greater than 9. Greater than 9 is going to be these 3 columns. And there are 6 options total there. 4, 6, 5, 5, 6, 4, 5, 6, 6, 5, and 6, 6. 6 total options. So therefore, just as we had before, there are 6 outcomes of, we can say, 10, 11, or 12. That's greater than 9. So therefore, the probability of this event, F, is the size of F over the size of the sample space. Size of the sample space is always going to be 36 in this example. And we have 6, and again, it's the same probability, 1/6. Let's think about the sum being even. We'll call this event G. Go back to the previous page, and let's think about even here. So we're going to be looking at 2, 4, 6, 8, 10, 12. And we're going to count all of those up. So there is one thing that's one outcome that gives us a 2, 3 that give us a 4, 5 that give us a 6, 5 that give us an 8, 3 that give us a 10, and 1 that give us a 12. I know there's a nice symmetry in this sample space as well. You have the most things around 7, and it goes away as you get further away from 7. So if we add all of these outcomes together that give us an even number, we get 1 plus 3 is 4, plus 5 is 14, plus 4 is 18 total options. So here the probability of G is going to be over 36, as we had before. Now there are going to be 18 options, and that's going to be 1/2. So note that you should have just assumed that, half are going to be even, half are going to be odd. There was some work that we had to do to show that, but in this case, it is 1/2. And now let's think of a more complex problem. We'll call this event H. The sum is even or greater than 9. In fact, we won't even call it H. We'll call it something else in a second. We're looking at the sum is even, which we know is the event G, or greater than 9, which we know is the event F. When we talk about or, we're talking about the union of those two sets. So here we're talking about G union F. We want to find the probability of G union F. Well, note that's going to be the size of G union F over the size of the sample space. And the size of the sample space is 36. So let's think about G union F. Sum is even or greater than 9. So that's going to include everything that is greater than 9. So all those options, and as well, everything that is even. So we're going to have all of these options as well. If we add them all together, we have a 1 here, a 3 here, 5, 5, 3, a 2, and a 1. It's going to give us a 20, which we can reduce to a 10 over 18, or a 5/9 probability. So note that the way that we counted the number of elements in G union F was something we could just call brute force. We looked at all the possible outcomes, and we just manually looked at all the different ones. But there's a better way of doing that, because we have a formula that helps us find the size of this set. We know this is equal to the size of G plus the size of F minus the size of the intersection. And we already found the size of G. We know that was 18 from part C here. The size of F we know to be 6 from part B. So really the only question is, what's the size of G intersect F? That is, the sum is even and greater than 9. So if we look at that, that is just going to include these 4 options. That is giving a 10 or a 12. And if you look at 18 plus 6 minus 4, you get the desired 20. And I erased the answer here. So although we could just do this by brute force, there's a simpler way of doing it, and that is looking at the counting methods that we learned in set theory. And this is getting into a more general idea that these equations that we have for counting in set theory work for probabilities as well. We saw the use for a union and intersection in the previous example. We can deal with complements as well. And we have 3 kind of formulas we're going to look at. One, the one we just used. The size of the intersection is the size of the size of the union is size of A plus size of B minus the size of the intersection. And this is the exact same thing as the probability of A union B. Is the probability of A plus the probability of B minus the intersection. Similarly, we have a nice formula for the complement. The size of A complement is the size of the entire sample space minus, actually I should say here should be U, right? The size of like the universe minus the size of A. And here, the probability of a complement is going to be 1, that is everything. That's like 100% of stuff, minus the probability of A. And note that if A and B are mutually exclusive, then A intersect B is the empty set. That means that the probability of A intersect B is 0. So we get a more simple formula if they're mutually exclusive. The probability of A union B is just adding up the two probabilities. This should be lowercase p's here. So let's look at some examples to finish out this video. Again, we're looking at a pair of dice. Find the probabilities of the following events. The sum is not greater than 8. So this is going to be the probability of greater than 8 complement, not greater than 8. So this is going to be 1 minus the probability of greater than 8. So if we go back to our chart here, to find how many things are greater than 8, that's going to be 9 through 12, which is going to be 10 outcomes are greater than 8. So if we go to our question here, this is going to be 1 minus our 10 outcomes over 36. Note if I want to combine these, I need to have a common denominator. So 36 over 36 minus 10 over 36 is 26 over 36, or 13 over 18. Now let's look at the sum is greater than 8 and odd. That is greater than 8, intersect odd. If we go back to our table here, if we look at greater than 8 and odd, we are looking at the 9 and the 11. That is 6 outcomes. So going back to our problem, this is going to be 6 over 36, or 1/6. So now let's look at the probability that it's greater than 8 or odd. Which is going to be the union of those two things. So therefore, we know that this is going to be the probability of greater than 8 plus the probability that it's odd minus the probability of the intersection. And we know some of these probabilities. We just found the probability of greater than 8 is 10 over 36. We know the probability of the intersection is 1/6. We'll go 6 out of 36 just to keep everything in terms of 36. And the probability that it's odd, well, we found the probability of even is 1/2. Probability of odd is also going to be 1/2. You can verify that on your own. Or we can think about that as 18 over 36. There's 18 possibilities that we have odd over 36. So therefore we have 28 minus 6 here. 10 plus 18 minus 6 over 36 will give us a 22 out of 36. 11 out of 18. All right, let's move on. Now let's look at a standard 52 card deck of playing cards. and we're going to draw one card. One card is dealt. What is the probability of the following events? We have that the card is a king and the card is a diamond. So we have the card is a king, represented by a K, and the card is a diamond, will represent with a little diamond shape. So we are looking for the probability of king intersect diamond. So note that if you're a king and a diamond, this is really just the exact same thing as the probability of getting the king of diamonds. And there's only one king of diamonds, so there's going to be one outcome. We'll say one card over 52 possible cards. So our probability is 1 over 52. So what is the probability that the card is not the king of diamonds? Part B here. Well, that's going to be the probability of this set that we just found complement, which is going to be 1 minus 1 over 52. I should say 1 minus the probability of the king of diamonds, which is king intersect diamonds, which is 1 minus 1 over 52, which we can reduce to 52 over 52 minus 1 over 52, or 51 over 52. A good chance that the card is not the king of diamonds. And now let's look at the probability that this is going to be a king or union a diamond. Using our formula, this is going to be the probability that we have a king plus the probability that we have a diamond minus the probability of a king and a diamond. We'll note that we just found this probability. That was 1 over 52. The probability of a king, well, there are 52 total cards, and 4 of them are kings, so 4 over 52. And the probability of a diamond, again, there are 52 total cards. There are 13 of each suit, so 13 over 52. We add the 4 and the 13, we subtract the 1. That's going to give us a 16 over 52, which you can reduce to 8 over 26, which you can reduce to 4 over 13. And one more example here. A company manufactures CDs. A recent sampling of products found that 5% have a defective case, 3% have a defective disc, and 7% have at least one of these defects. So let's find the probability that a product has both defects. And let's call these things, let's say that we have a defective case. We'll call that C for case. Having a defective disc we'll call D. Having at least one of the defects is going to be C union D. So find the probability that a product has both defects. We are looking for the probability of C and D. And note that the probability of C union D is the probability of C plus the probability of D minus the intersection. So if we add the intersection to both sides of this equation and subtract the union, we get another equation we can use. The probability of C intersect D is the probability of C plus the probability of D minus the union. So here we have the probability of C is 5%. Probability of D is 3%. And the probability of the intersection is 7%. So we're going to add the 5 and the 3, subtract the 7, and that's going to give us a 8 minus 7, which is, 1%. Another way that we could have done this is to draw a Venn diagram to show the possible defects. So let's draw our Venn diagram. We have all possible products. We have our circle representing C here, and our circle representing D. And we know that the union is, or we can say, the union is 7, the size of C is 5, the size of D is 3. So just kind of thinking about these together, if we know that 7 is the total area, the total things inside both circles, and if we subtract off the number of things in the defective disk in D, that should leave us with what's in just C. So in just C, we're going to have our 7 minus what's in D, 3. That's going to give us our 4%. In D, we're going to go 7 minus what's in C, 5. That's going to give us a 2%. And that leaves a 1% in the middle. So then we can use the Venn diagram to think about what is the probability that a product has neither defect. That's going to be everything that's not in those circles. That's going to be 100 minus 7, or 93%. And if we use this using probability rules, this is the probability of C union D complement, having neither C nor D. And that's going to be 100% minus the probability of C union D, which is 100% minus 7%, 93%. So note that we've really what we're doing with probabilities is counting. We're doing a lot of the same ideas we've done with counting. We can use Venn diagrams. We can use these formulas using intersections and complements and unions. And really what we're doing is just adding one other detail, which is we're putting it as a fraction over the total number of possibilities.